Hi everyone, good morning. I think the chat is active today. I saw there are questions there, right? Anyway, we will go through that later. Okay, so today we will uh, covers the topic called time response, right? So from the previous sessions, we have mentions about how to model and convert the model, mainly the mechanical model, into transfer functions, right? Then from the transfer functions, we form the blocks and we learn how to simplify a block diagram, okay, into a simpler one, right? So today our task would be now to analyze what would be the response of that transfer functions, right? So our main task today is to see to address the course outcome number 2, which is to see the transient response, how they respond to an input, okay, and how we can make use of it, okay, later on, right? So now, as mentioned, there is questions about what is Mac OS for. Alright, okay. So this is a software, okay, called Scilab. Okay, so the latest version that I have seen, if not recently, is 6.1.0. Okay, 6.1.0. Okay, and then usually we will couple it with Xcos, okay, which have been pre-installed. Okay, once you install the Scilab, make sure you just don't remove this package, so-called package. Okay, you just make sure you take the Xcos so that it will install together. But usually if you use the default, it should be installed automatically, right? So here is the different users of computer. So you may have using Windows, okay. I guess most of you are using Windows, so you don't have problem with that, all right, especially regarding bugs and so on. So yeah, you just download the Scilab from the website given, okay, and then you just click through the link, okay, download Scilab, okay, Scilab, okay, and then depends on your Windows versions and your CPU. I guess nowadays, if you bought your computer in the last 2-3 years, your CPU, your Intel or AMD should be able to support 64-bit, right? Whereas if you are a Mac user, meaning Apple MacBook or whatever it is user, then you have to refer to the Mac OS, right? So Mac OS is the operating system for the Windows, for the MacBook and so on, okay. So if you are using that, then you need to install several additional things, okay, in the sequence, right? So you may have to install the Java development kit first, okay, through the link. Then only you install the Scilab, and then because of the security features, they may not able to access your computer folder and display it. That's why you need the third step to enable it, okay, so that you can select your folder from your Scilab itself, right? Okay, so if this Scilab is open source and free, so that's why we will try to use this one, okay. Whereas if you have a student versions, or you can access the MATLAB through the remote desktop, okay, to university's server, then you are welcome to use the MATLAB, okay, and plus Simulink, right? So the features and the functions are similar, okay. So MATLAB and Scilab is the core program, right? Whereas the Simulink and Xcos is the package, okay, that they built on top of the MATLAB, okay, to do the calculations and so on. Right. Yes, Mac OS is just an operating system depending on which type of computer you are using. If you are using Apple product, then you have to refer to Mac OS. If you are not using, like maybe you are using Asus, HP, Dell, and so on, when you boot, you see a window logo, okay, Microsoft Windows, okay, that would be your Microsoft Windows operating system, Windows OS, right? So it depends on which type of operating system you are using, right? So you install accordingly, but the interface after you install should be similar, right? So this is how you can solve simultaneous equation using the software. So Scilab and MATLAB actually built based on matrix. Okay, the foundations are matrices because the main idea is to solve multiple equations. Okay, so you can see that if you want to solve a simultaneous equations, if you can group them into a matrix, okay, in the form of A multiplied by X equals to Y, okay, a familiar form for you, okay, then you can actually get the solutions of X, okay, by taking the inverse of A multiplied by the Y, right? So you just have to define what is the A matrix and the Y matrix, right? So how to define, you can just start up your computer, okay, after you install, you should be able to open the Scilab, alright? So this is what I mentioned, okay, for Mac OS, you may not able to display the folders, okay, in the Scilab itself, okay. After you do the step 3, then you can show all these folders inside your computer, right? Inside the Scilab, okay. So very straightforward, okay. If you don't want to do the save of the file, okay, then you can just directly type, okay, in this console itself, okay. So this console is where you do your operations directly, okay. So you can type define what is your A. So if you type A equals to so on, Y equals to so on, okay, then you can type X, you do this operation, X equals to the inverse of A multiplied by Y, then you can get your X answer. That's it, okay. Very straightforward, right? So all this software is just a tools to helps you to solve the problem, right? So regardless of what software you use, you want to use MATLAB or whatever it is, it's okay, right? It's just a tool, okay. Remember, all this software is just a tool, okay. Only depends on whether they are more efficient or less efficient and so on, okay, in terms of computational time and other things, right? So basics of Scilab, right? Since Scilab actually developed to give the so-called free and open source type of experience to other users beside MATLAB, right? So they are actually built very similar in terms of command and interface, okay, between Scilab and MATLAB, right? So you can always Google it, okay. The command is almost maybe 95% similar, right? So if you learn this, okay, when you want to use MATLAB, it would be very easy, right? So it's just a matter of the signage and so on, right? But basically they are 95% similar, right? So let's now talk about how to generate matrix, okay. So you can generate a row of vectors or matrix by just typing A, okay, equals to 1 dot dot 5, okay. So it will generate like 1 2 3 4 5, okay, from 1 to 5, okay. You just put a semicolon there, right? So if you want to generate with a step, okay, so you will see that 1.1 is your starting value, 1.5 is your end value, and 0.1 will be your step, okay, how much you want to jump. So since I put 0.1, so every time it will jump from 1.1 into 1.2 1.3 and so on, okay. Then you can also, if you have multiple matrix, already exists in your memory, okay, then you can combine them together. You can put C equals to A. If you put dot and comma, okay, so if you put this sign, right, so if you break it into a second row, right, second line, okay, so you have to know that this symbol represent a break in row, okay, in the matrix itself, okay. So you will see that if you put in this way, okay, since this generate one row of matrix, another row, so if you put this, combine them together, you will see your matrix in this form, okay, in two row, okay. So always try to type, okay, and check, okay, what is the result. So once you type, you enter, it will generate this result for you. So this is actually a screenshot, okay, from the software, okay. I just try and show it here, right. So you can always try your own value, okay. Next would be how you can identify or extract the exact value from that matrix, okay. So let's say now in A you would like to know the third number, okay, first, second, third, okay. I don't care what is the value, but I want to know the third member, okay, what is the value of that, okay. So if you type A bracket the member number, okay, the counting of the member, then it will shows you the answer, okay. It refer to number 3, okay. So if you put 3.5, meaning to say you are selecting member from 3 to 5, okay, this double dot, okay, refer to 3 to 5, okay, you get this answer, right. So again, if you put like this, okay, for the first one, then comma the second one, then you are referring to this is row and this is column, okay. First row, the row and the column, and this dot, if you don't put anything in front and back, you need to say you're selecting the whole things, okay, and this represent the column, right. So same thing with the others, right. So it's very straightforward in terms of how you manipulate the matrix in the software, right. Again, now you can start to put in polynomial, right. So you can put your so-called equations into your software, okay. So in order to for the software to recognize which one is your symbol, okay, so you have to put x equals to poly bracket 0 and then your x sign, okay. So from that onwards, the software will recognize that this x itself is a symbol or the variable that you are going to use in your polynomial, right. So you just put this line, okay, to define what is your variable, okay. You can put y or z or h or a or whatever it is, all right. Then after that, now you can start to type your equations, right. So you can type your equations, okay. Equation, let's say d, okay, equals to, now you can type your x, okay. So the software will not prompt an error, okay, because the software now recognize that x is a variable, okay. You don't need to put any value, so they will not do any calculations on this equation, even though this equal signs tells the software to calculate, okay. But then since they know that this x is a variable, so they just display that in form of polynomial, right. So they will just rearrange from the lowest order to the highest order of your variable, right. Then also you can identify what is the coefficient, okay, of this d, okay, so that you know this is the coefficient, okay. The first one, the second one is 2, the third one is 1, okay, and so on, right. So that would be helpful when you trying to program it, okay, in the future maybe, all right. Also you can solve this polynomial quickly, okay, by typing root bracket your polynomial, right. So it will display the answer, right. So since this is a second order, they will generate the answer for you. Okay, so the roots for this polynomial would be this and this. Okay, hopefully it's correct. You can double check, okay, by using your knowledge of mathematics, okay, and check it out, right? So this is how your basic knowledge, okay, your mathematical knowledge, your control engineering knowledge, and so on, okay, would be helpful to verify, okay, or validate all the results. Okay, just for example, if this root somehow the value is wrong, okay, meaning to say the software have bugs, okay, there is some problem with the software. This is how we can identify the bugs. Okay, don't accept whatever generated by the software. Okay, sometimes after generate several times you feel that the result is weird, then you have to do your manual calculations, okay, and compare. Okay, so that this is how you can validate and make sure that the software is not doing wrong or your command is not doing wrong. Okay, because whatever you enter will be outputted. Okay, the software will not tell you this is the correct step or not, right? They just output whatever it is. So sometimes maybe your command is wrong, right? So this is why you need to validate, okay, using your basic knowledge, right? So once you are familiar with that onwards, then future it will be easy for you to actually use it, right, without doubts. Okay, then also you can try with this. Okay, so this is how you can assign your polynomials, right? Okay, so you can start to put like transfer functions, like if you don't want to put x, you can put s. Okay, s. Okay, so it will form like a transfer functions for you, right? Then come to the software called Xcos, okay, or in the MATLAB side would be the Simulink, right? So this is a so-called a visual or with a graphical interface. Okay, so you just go to the Scilab, all right, then you look for Xcos. Okay, Xcos, right? Then you will see that you have you will be presented with this palette, okay, or browsers of those diagram, okay, that you can use. And here is your playground, right? Okay, your empty space, okay, where you can drag. Okay, so now what you need to do is you just drag, okay, the corresponding blocks that you want, okay, to form your block diagram, right? So if you can simplify a block diagram, then the number of blocks that you have to put in will be lesser, and so on, right? Okay, so that's why MATLAB, Simulink, Xcos, and so on are very useful tools for engineers, especially in the signal side, okay, the communication side, and so on, okay, to analyze how the signal actually change, okay, and so on, right? So what you need to do is you just drag, okay, just drag, okay, and drag. So how to display the result? You use a cam scope, okay, so you can use a C scope over here, right? And this C scope, since you need the time for it to plot, so you put a timer over here, right? So that when this time take maybe 1 second, okay, or 0.1 second, depends on your setting, then you calculate a value for you, okay, then you plot accordingly. If you don't put this timer, then your time doesn't move, so you will not plot anything, right? So this is your source, okay, so you can go to source and drag this out, okay. Then if you want to modify the parameter inside, you just double click, right, or right click of it, right? So double click of it or right click of it and edit it, then they will be displayed with this kind of blocks, okay, where you can modify, right? So this is the block, okay, the summations block, okay, and this is the parameter you can put in, so you can see that this is plus and minus, right? Initially maybe plus, okay, you may not able to find this, okay. What I did is I put inside 1 and -1, so that they will know this is plus, this is minus, okay. So you can try with that, right? Then on the transfer function, again, you just double click, okay, then you can start to type, right? Since the value s, okay, or the variable s is well known, okay, throughout the control engineering, so you don't need to define this s, okay, you like the way you start with typing, right? Because in the typing part they solve the general mathematical form, but in this form they know this is transfer functions, okay? So what you need to do is you just drag it out, okay, double click it, okay, then you can start to put in what is your numerator, the upper part, and the denominators, right? So you get your transfer functions, right? Then you will have a run button sign, okay, a triangle run button sign at the top, okay, of your Scilab Xcos. You click run, then you will see this graph, right? That's it, very straightforward, right? And this is what we intend to see today, okay, how it would respond, okay, to the time, and we call that as a time response, okay? For sure you can always look for helps, okay? Helps, you just shout helps in your software, right? By typing help, okay? You can type help, then they will display with the help menu, okay? If you know exact command or functions, let's say you want to plot a board diagram, okay, or you search internet, they say you can use these functions to do certain things, okay? So what you can do at that time is that you just type help space your command, right? Then they will display what is the input output parameter that they can accept, okay, in that particular functions or command, right? That is how you can shout help inside your software, okay? Scilab, MATLAB, exactly the same, right? Now back to today's missions, okay? Our target is to see the time response, okay? So for a system's response itself, you can break them into two type of response, okay? The first one would be the force response, which would be the steady state response, okay, because your force may somehow constant at one time, right? So that force will give you a so-called steady state response at particular time, okay? Whereas the natural response would be the response within the system itself, okay, just like the example of the ruler, okay, that I give a long time back, okay? When you flip the ruler, okay, then it will just oscillate, okay, through their own natural response of frequency, okay, and that would be the natural response of it, okay? So when we combine these two things together, we will form the total output response, okay, for our whole systems, okay? In order for us to analyze this system response, one of the fundamentals concept would be using the pool and zeros, okay, the pools and zeros, okay, to evaluate how, based on this pool and zero, what we can tell, okay, from the transfer functions and how it would respond to the time, okay? So that is our missions today, okay, to analyze the time response by looking at the poles and zeros, right? So what is poles, okay, what is zeros? So the poles referring to the solutions, okay, or the roots for the denominator, the bottom side, okay, that would create a pool. All right, so in this Laplace transform, or let's say this is a transfer functions itself, okay, so whatever values that turns this into infinity, okay, like a globe, okay, turns into the pole side, the infinity side, we call that as a pole, okay? And in order for us to do that, you have to make the bottom equals to 0, right? Meaning to say you are finding the roots for the denominator, okay? Very straightforward, okay? So you have s equals to 0, right? S equals to 2 and s equals to -3, okay? That would be your pool, right? And when you want to represent it into the S-plane, okay, we call this as S-plane, right? Remember this, S-plane. So you just draw the imaginary, okay, so the vertical axis would be imaginary axis, and this would be the real axis, right? So this pole will be plotted on the the real axis, okay, since the solutions for this value is all real value, right? Real value, okay, that's why we only plot on the real axis, okay, where imaginary value is equals to 0, right? So that is the first thing, the pole. Then second would be the 0, right? So the pole we put x, okay, the small cross sign to represent the pole, whereas for the zeros is whatever values that form or convert this transfer function become 0, right? Very straightforward. So meaning to say we are finding the roots at the numerator parts, okay? So here if we put 2, then our numerator will become 0 and our whole transfer function will become 0. Alright, so here we will represent it again, since the solutions is 2, okay, real number, okay, no imaginary number, so we just draw it on real axis, okay, with 2, okay, with a 0 sign of it, okay, to denote the 0, right? So this is how you can plot the pole and zeros on the S-plane, right? Now again, we would want to know, okay, what is the time response, okay? When we are looking for the time response, we are basically trying to solve our transfer functions and take an inverse Laplace, okay, inverse Laplace to form back our equations in terms of time, right? You have to turn it back from the Laplace form into the time form, okay, so this is our time response, okay, where our values or our functions will be in terms of time, okay, and you can see that in this time response itself, it consists of 2 parts, okay. The first part would be the force response, okay, which is independent of time, okay, whereas the second part will be the natural response, which it will keep oscillating according to time, right? So that would be the force and natural response, okay. When we combine that, we form the time response for the whole system. All right, so here what we can see is we just take an examples of this, okay. We have a simple transfer function of s plus 2 over s plus 5, and if we would want to represent that into S-plane, then we will draw it in this way, right? Immediately we know the pole is -5 and the 0 is -2, okay, and we know that this transfer function is subjected to an input, a step input, okay. Remember, step input, the value will be 1 over s, okay. So in general, we would not tell you what is the value of to be input over here. We will just say give a step input or unit input, okay, or impulse, okay. So you have to know all these terms, or ramp input, right? Then you would know what is the value you should put in, right? So but then in this whole sessions, okay, we will only deal with step input, okay, step input, right? So our RS value will be 1 over S here, okay. So now what I try to show here is just I can also try to use Scilab, okay, Xcos, okay, to do it and plot this curve, right? So this is the curve that I get, okay, from by putting a step input. All right, then I can also try to actually plot them out, okay. If I don't want to use this one, okay, I can type, okay, my command, right, to plot once you have all these equations, you can actually type, right? You can try to type, okay, and check, okay, this is what is this, okay, and you plot, okay. So eventually you see that this curve, okay, this time response generated by this is exactly the same with this, right? The total of the time response, right? So this is just to show that it's able to generate the same results, okay, to validate it, okay, somehow. Okay. Then next would be the how we can draw from that particular. Remember, our missions today is to use the pole and zeros to tell us something, right? How it will form those so-called response, okay. So what we can do now is that you can see, okay, from this zeros and poles, okay. So again, this is the command, okay, that you can try, okay, to generate the S-plane in Scilab. Alright, so I don't draw, okay, I just show this, okay, in generated by S-plane. But later on, when you are dealing with exams, or when you want to use hand to write, okay, then you should always plot like this, okay, just two axes with the sigma, okay, to represent the real, and this j omega to represent the imaginary axis, okay, just two axes, and then you plot it out, right? Okay, so again, back to here we can see that the transfer functions have a pole, right, that corresponding to the natural response, okay. And this natural response, now if we break them out, okay, here we can have several informations, okay. First thing is we don't look at the input first, okay. We only look at these transfer functions, and these transfer functions, we have the system 0, okay, there's our system 0 as -2, and our system pool as -5, right? So this is -5, this is -2, okay. Whereas this input, okay, will give us an input pool, okay, since this represents 0, okay, this will be input pool over here. So what it tells us is that from these combinations of zeros and poles, okay, you would now see that, okay, here this 0, okay, this 0, okay, will affect the value at the top, okay, then the numerator part, right, the values at the top, okay. Whereas the pole, okay, the pole will now detect, okay, or define our fractions, right? Remember, you have the forced response, the natural response, and so on, right? So this input pole will correspond to this 1 over s, or a constant over s, okay. Whereas this pole, you will get this value, okay. And this fractions, okay, when we convert it back to the time response, then it will be corresponding to this exponential terms, okay. Exponential, this is +5, then you will get -5t, right? So that immediately tells us this part, right? So we can break them into two parts, okay, and we can now see actually how this pole and 0 when they combine together will affect our response, right? So the input pole will affect the force response, whereas the system pole will affect our natural frequency. So your system pole may have one, okay, if this is first order, if you have second order and third order, then you have multiples exponential terms or cosine terms, okay, as the natural response itself, right? Then the zeros plus the pools, okay, that will tells us the k value, okay, the amplitudes for both of these, right? Okay. So now again we go through an examples to quickly illustrate the concept. Alright, so we have this transfer functions and being input with step input, right? So immediately if we want to just write the form of partial fractions, okay, that we can create, okay, to corresponding to this response, okay, in the Laplace form, okay, we would have this as k1 over s, okay, plus k2 s2 k2 s4 plus 4 and k4 over s plus 5, okay. So that this would represent the natural response, and when we take the inverse of Laplace, then we will have this as our forced response, whereas the rest, okay, you can see that this is -2, -4 and -5, okay. Immediately we will get this this time response form, okay, mainly based on the zero, the pole itself, okay. This is how it is useful, right? And again, you can see I can generate immediately, okay, the type of response it is, okay. So and this curve represent these equations, right? So these equations will tell us how it will behave, okay. When we put in a step input, okay, this is how it would behave, right, towards the end. Okay, so I hope that would clear your first part, okay, how we can see the importance of zero and poles. Okay, then next we will start to slowly analyze, okay, the first order system. After that, we will analyze the second order system, right? Again, mainly based on zero and poles, right? And what type of information we can extract to define the performance of the system itself, right? So here is a first order system, okay, a general first order systems, okay, which have constant, okay, a k divided by s plus a, okay, and then we give a step input, okay, a unit step, right? So remember, again, for these sessions we will use a step input, okay, and this is a very important first step for us to analyze, okay, and characterize our system, right? So you have 1 over s and so on. So this would be a constant, right? So if this is a constant k, okay, we can always change it to so-called a by taking out the remaining factors, okay, or we factorize out a certain constant, okay, so that this value of a, okay, this a should be equals to this a. Okay, this is our main first task, right? So if you see, this is, let's say this is s plus 5, okay, and upper side the constant is 10. What we can do, we will put 2 multiplied by 5, we still get 10, right? So that 2 we factorize out, okay, then we have 5 and 5, exactly the same, a and a, right? So we would try to form this general form first, okay, for us to actually analyze it easier, okay, in the later stage. Okay? So once we have this form a over s plus a, then immediately we will get this value, right? E minus at, right? Whereas the 1 over s over here corresponding to 1, right? So this is the way you can do it. So if you factorize out the 2, then the whole thing multiplied by 2, that's it, right? Very straightforward, okay. And also if we plot it out, okay, then we have this the S-plane diagram, right? So we can plot it out. This is the S-plane diagram and this is the the so-called the block diagram of it, right? So transfer functions of it. Okay, so this is how we can represent our first order system. Then once we have that form, then immediately we know that would be our solutions, right? Very straightforward. Okay, 1 a over s multiplied by s plus a, and you will get these solutions. Okay, immediately, right? So from that solutions now, okay, we try to see, okay, if we put t equals to 1 over s, so that this exponential term is in the order of -1. Okay, if we put that t equals to 1 over a, okay, when time equals to 1 over a, we would notice that this value become 0.37. You just press your calculator, you get 0.37, and if we take 1 minus this value, we will get a 0.63. Okay, 0.63. So this 0.63 now will tell us a meaning that from the final value, okay, final value, initially our final value is 1, right? Okay, but as time increase, okay, then it will actually approach 1. Okay, but when time is 0, okay, then it would give us another value. Okay, so this is the 63% of the final value, and that occurs when time equals to 1 over a. Okay, so this is an important characteristics. Okay, so we will later on we will start to use all these basic characteristics of the equations, okay, to actually identify or define the transient response, okay, how it responds to, or to describe the specifications or the performance of this system. Okay, we would use 3 terms. Okay, the first one is the time constant, the second one is rise time, and the third one is settling time. Okay, so remember these functions or this equation, 1 minus e to the power of minus at, okay, is a first order system's response, and we would want to know what is the time constant, rise time, and settling time, right? So by doing that, now if we varies all these parameters, okay, or if we varies this a, all right, so it will actually change the speed of the response. Okay, how fast is rise, okay, and how fast is settle to the steady state, right? So we want to know, okay, how it change according to that. Okay, so this is the first important specifications, okay, of a first order system. We call it as time constant. Okay, I believe you saw time constant in thermodynamics as well. Okay, it is referring to the response of your system to the time. Okay, and we define the time constant as 1 over a. Okay, remember previously we put time equals to 1 over a. Okay, and that is the time constant. Alright, we always remember the time constant is 1 over a, and when time equals to 1 over a, what happens is that it's actually 37. Okay, remember 0.37, okay, which is 37% more, okay, before it reached the final value. So assuming the final value is 1, okay, so meaning to say it has already increased 63%, okay, but you still left 37%, okay, to reach the final value when we input a step response. Okay, so remember the previous equation still corresponding to the step response, okay, or the step input. Okay, so because of that, now what we can do is from this final value, we take 63% of this value, okay, which is 0.63, okay. Then when we draw this line down, okay, we will get this time, okay, and this time is actually corresponding to 1 over a, okay, which is the time constant, okay. So this is the characteristics of the time constant, right? So again, you can see this is the value of it, okay. This blue line, all right, is exactly this line, all right. So I just regenerate it, okay, using Scilab, okay. And you can see that if I'm using impulse signal, then you will get the green one, okay. Immediately you know that something is wrong, right? Because you are putting the wrong input, okay. You can see that when the input is different, the characteristics is different, right? So for this case, our characteristic is the blue one, okay, the blue one. And now what we can see is that if this is from this idea, okay, from this idea itself, 63% we will get the time constant, okay. So we will see that if this is the final value is 1 again, right, for the blue line, right, then if we take 63% of it, okay, which is 0.63, I just approximate 0.63, okay, and I draw it down, I will get 0.5, okay. So 0.5 is my 1 over a, my time constant, okay, meaning to say that a equals to 2, right? So immediately I know the transfer functions should be 2 divided by s plus 2, okay, which is correct, right? Because this curve I generate using 2 divided by s plus 2, okay. So this is how we can check, okay, whether it is correct or not, right? And at the same time, you can from the equations, from the transfer function, you can generate the graph, or vice versa, okay. From the curve, you can regenerate the transfer functions, okay. So we will call this A as exponential frequency, okay? Exponential frequency. And we always use a step input to characterize this time constant, okay. We don't use impulse or ramp input, okay. We use step input to characterize this time constant, okay, to see how it respond to the input, okay, for this so-called first order system, okay. And this exponential frequency, this A itself, mainly depending on the pole, okay, the pole, right? So from the pole itself, now you can actually extract this value out, right? The second performance specifications for a first order system will be the rise time, okay, how long it takes for it to rise, okay. And our definitions will be for it to rise from 10% of the final value to the 90% of the final value, okay. So this 10% before and after is to remove the so-called extreme value, okay, at the both end, right? So we will want to know 10% to 90% how long it takes, okay, how long it takes. So it's very straightforward, okay. Just plot it out, okay, then get the line, and from there you measure, right? So once you measure, you will get the rise time, okay, the rise time of it. And since again this is the first order systems, okay, the rise time can be defined as 2.2 divided by a, okay. If you don't believe this value, you can try it out, okay? Eventually you will get 2.2 divided by a, right? Based on this value, okay? So this would be 2.31 over a, and this value is 0.11 over a. So you get 2.2 over a, okay? For a first order system, the rise time is that, right? Next would be the settling time. Settling time referring to the time it requires, okay, from zero, okay, from initially zero value, now we put in an input, a step input. So because of this step input, the system has to respond and move to 1, right? Okay, as our final value. So how long it takes for it to actually reach the steady state, okay, we call it as a steady state region, okay, and we usually define as 2% of the final value, okay, meaning to say we want it to be 0.98, okay, within the 0.98 and 1.02 range, okay. For this time, since this is first order, immediately we just set this as a 0.98 value, okay, because it will not cross the final value of 1, okay. This is the characteristics of the first order system, okay. It will just shoot up, okay. You can see the shooting up is straight, okay, no curve, straight, and then only it curve and becomes steady, okay. No oscillations at the higher, near the final value itself, right? So we get 98% of it, okay, and we eventually get this value at 4 over a, okay, 4 over a, right? So 4 over a. So you can see that the importance of this exponential frequency itself, the a value itself, okay. By knowing all this, by knowing the exponential frequency, the a value, okay, basically you don't need to plot all these things, okay. You already get the settling time, the rise time, okay, as well as the time constant if you want, right? So that is the importance of knowing what is the pole, okay, and then what is the time constant, and from that you will get the settling time and rise time to define the performance specification for your first order system, right? Next would be how we can do the inverse part, right? I guess I have somehow reviewed these methods, okay, previously, okay, because most of the time, let's say the performance of a certain device, okay, we are not knowing what is the transfer functions, okay. You don't see any equations, okay, no equations on your device, right? So how we can tell what is the response of the device itself, okay? Either you can analytically solve it, alright, or another way is you do empirical methods, okay, meaning to say you do a testing, okay, and this is how you can do the testing, okay, to review or to obtain the transfer functions of it. So how we can get the transfer functions by doing testing is that, remember, we can obtain the curve, okay, as long as we do a testing by inputting a step input to our system, okay. We inject a signal of 1 over s to the system. So let's say this is the device that you intend to know what is the transfer functions, okay. So you give a 1 over s signal to it. So let's say maybe you want to know how fast it responds to to the movement. Okay, so you give a 1/s signal to it, maybe a kind of positions movement to it. Okay, and you now capture how fast the cursor actually move from one point to another. Okay, you plot into a curve, okay, a graph, right? So from that graph, okay, from this curve or the graph itself, you can reveal the time constant. Okay, from the time constant itself, now you can know the settling time and so on. Once you know the time constant, basically you also know the equations by putting it back, right? So if you get the time constant, okay, you can solve this, right? So that is the idea behind doing a testing for an unknown object by injecting a step input to it, okay, and plot the outcome of the output curve. From the output curve, you find the time constant of it. So once you know the time constant, the a value, now you can regenerate back the first order transfer function to describe your device, okay, your tested device, right? So this is how you can find the a itself, okay, from the final value. Okay, let's say this is the final value, 63% of it, okay, which is roughly 45, okay, 0.45. Okay, so from 0.45 we get this value, which is roughly 0.13 second. Okay, then we get the a equals to 7.7. okay, so once we get 7.7 as a, next we can get the k value. Okay, the k value, what we need to do is we know the final value, okay, and that final value corresponding to the first part, okay, the constant itself. Remember, we have 1 minus e minus at, right? That one we assume when the k is equals to 1, but you can factorize it out, right? So when you factorize it out, you have a k value basically. So what you need to do is that k over a, okay, when you factorize it out, the k over a is referring to your final value, okay, which in this case is 0.72. So we already know a is 7.7 and the final value is 0.72. From that you can solve for the k. Once you solve for the k, now you know the transfer function by just doing this test, right? So far, any questions before we move to the second order system? Okay. If you have questions, do post it on the comment in the chat box. Okay. While waiting for the questions, I think we will move on or proceed to the second order system. Alright, so from the first order system, we know that the time constant is a very important value for us to define the performance specification like time rise and settling time, right? Now in the second order system, you can see that because it is second order, now it start to oscillate, right? You can see that there is undamped characteristics, okay? It doesn't damp out, okay? It always keep oscillating without slowing down, okay? Meaning to say no damping, right? So undamped system. Then the second one would be the systems is under a damping, so we call underdamped, right? So it still oscillates, okay, but slowly going towards a final value or steady state value, right? Then the third one would be a critically damped, okay, meaning to say it damped such that it doesn't overshoot, okay, it doesn't oscillate. Okay, you can see that this curve first it curve up, okay, and then it doesn't oscillate. Okay, you don't see the oscillation. We call it as critically damped, right? And then when it is even slower than that, we call that as overdamped, right? So you can see that even slower than the critical damp, we call as overdamped. So we can group the second order system, the time response for it, into 4 groups. Okay, undamped, underdamped, critically damped, and overdamped, right? So the 4 group of or 4 form of response, okay, for a second order system. Okay. The changing of the parameters that affect the response of the second order depends on 2 main parameters, which we will see later on. Okay, again, we now look at the relationship between the pole and zero with the second order, right? Here, this is a second order general equations. Again, we try to put that such that the numerator, the constant of it, b, is exactly the same with the value at the bottom, right? B over here. Okay, so this is again the general form of it. Okay, if you want, if they are not the same, you do some factorizations to factorize out a certain factors by multiplying it, right? Then you will have the same value of b over here, right? That is the main idea. And you can see that in this second order response, there are 2 poles. Okay, 2 poles. Okay, you have s square, right? 2 poles, but no zero, right? No zero. Okay. So what we can do now, we will do the same thing. We will inject a unit response, okay, a unit response or a step response. Okay, unit means 1, right? A unit response or a step response, okay, which corresponding to 1 over s, okay, to the system. Okay, we inject that, okay, to our system, 1 over s, okay, and see what would be the response, the outcome of it. All right, so in order to get this outcome, we just multiply them together, then do the partial fractions, we break them out, right, to identify what is the pool and what are the pools, okay, since we have 2 poles, okay, over here. Okay, and then we do the Laplace transform, okay, to get it, right? So you can see that if it is in this order, let's say this is in this order, we can now do the partial fractions expansions, okay, break them into 2, right? So immediately you can see that there is 3 poles, okay, 1 is due to the input and 2 is due to the system, right? And because of that, now we can start to see how it would map, or how it would correspond to the different form of response. Okay, the first one we would want to mention would be the overdamped response. Okay, overdamped response means a lot of damping putting on it so that it will actually respond, and but then it doesn't oscillate. Okay, if you observe this carefully, okay, this response carefully, it looks similar to the first order time response. Okay, if you look carefully, they are very similar to the first order, right? But the only difference is at the beginning, right? So in the second order response, it will still curve up in this way, right? Whereas for the first order, it will directly go up and settle, right? That would be the characteristic of the curve, okay, that you know. So once from that, you will know whether the system is first order or a second order. First order, straight up and no oscillations at the end, okay? Whereas for the second order, you have this small curve, okay, and then now they may start to oscillate, okay? But sometimes, because we are putting a lot of damping over here, we call that as overdamped, then it doesn't oscillate, okay, but it still behaves like a second order, right? Now what next would be, this is our pool zero plot, right? So since we only have the pool, then we have only these two dots, okay? We don't draw for the inputs, okay? We just draw for the system, okay? Just to show how it corresponding to the behavior of it, right? Since the input is very straightforward, right? So now we look at this, okay? We can always break them into partial fractions, okay? First, you have to solve this polynomial second order into this form, right? You solve it out, okay? How to solve, okay? Just go back to the mathematics, right? How to solve it, right? For a second order, and then we would notice that these functions now, okay, have one pole due to the input, okay, and two pole due to the system itself. And we notice that these two pole now, okay, these two pole are real pole, okay, real value, okay, real value lying on the real axis, okay? So when you have two real pole in the system, this is a characteristic of an overdamped response, okay, for a second order system, right? And that corresponding, these two real pole will corresponding to this exponential natural response, okay? You can write such that this is e minus same thing, okay, t, and then plus the e minus 1.146 t, okay? I missed the t at the end, right? It should be t at the end as well, right? So this is how you can form the time response, okay, immediately, right? So for overdamped, remember it has two poles. Yeah. Next, we will see the underdamped response. For an underdamped response, now you will see that it will start to oscillate, and you have a final value of 1. Okay, this final value of 1, you can see that the curve will start shooting up more than 1, okay, before it coming down and up and down again. So we have the overshoot characteristic of a second order, right? Because damping is not enough, we call it underdamped. You have this overshoot characteristics, and this corresponding to when you have a two complex pole. Okay, if you solve this bottom part, the solution of this s would be -1 plus minus an imaginary component. Alright, so you can try to solve this bottom part. Okay, you will get the imaginary part of it. Okay, and because of this imaginary part, when you plot it out on your S plane, you will see that it's not now lying on, it's no longer lying on the real axis. Okay, it's somewhere in between it, okay, which corresponding to -1 and plus j square root of 8 and -1 minus j square root of 8, right? So that would be your natural response, and because of this complex pole, you would get the undamped response. Okay, you will get this behavior, right? So if you compare it to the time response itself, the real part of the pool the real part of the pool is representing the decay behavior of it. Okay, how fast it decay to the steady state or the final value. Okay, whereas the imaginary part, okay, because of we have the imaginary part, this imaginary part will now tells us the frequency of these oscillations. All right, so this is how we can break it down. Okay, the exponential decay, okay, and the imaginary part, okay, which corresponding to the frequency of these oscillations. Okay, again, the time constant of this exponential decay, okay, remember the time constant, right? So this exponential decay time constant is 1 over the real part. Okay, 1 over the real part. Okay, what is your real part here? Your real part here is -1. Okay, so it's basically 1 over -1. You get -1, right? So that would be the time constant for your exponential decay. So if you plot that curve out, you will see that form this line, and that form the so-called envelope. Okay, you wrap it inside this line. Okay, this envelope of exponential decay curve. Okay, and these oscillations will always oscillate within this envelope, right? So same thing with the bottom. Okay, so you have an envelope of this exponential decay, right? Whereas the frequency will tells us the sinusoidal, the frequency of it, right? And eventually, due to this step input, okay, your input is going in from 0 up to 1 and straight onwards. Okay, since your input is also a step, okay, after that it remain the same value. Okay, therefore you will reach a final value. Okay, a final value. Okay, because you no longer push it, right? Meaning to say you give a constant force to it. Okay, the force may be 5 Newton, right? So that is the constant force. Okay, so eventually it will reach a steady state conditions, right? Here is an examples, a quick examples how we can immediately see what kind of form of the time response when we give a step input. Okay, what we can do here is we check the upper part, the constant, right? So since this is the same, then great, right? Then next we would just solve this part, right? Break them into the solutions, and from the solutions we want to know whether it is imaginary or real. Okay, it is a complex solutions or a real solutions, right? And eventually we get, for that examples, for these examples, we get complex solutions for our denominator, meaning to say immediately we know the response would be underdamped, right? The underdamped response. And because of this underdamped response, we can also obtain the equations or estimate the equations of it, right, by putting into our equations, right? So our solutions would be in the form of our constant, okay, which corresponding to the input, the step input, plus the e to the power of -5, okay, bracket k cos this value, right? Since this is plus and minus, then you have also the sign part, right? So you have cos and sine, plus and minus of it, right? If these two values are different, then you have two part of it, right? So that is the straightforward part of forming the time response equation based on the familiar form of the transfer functions for a second order system, right? Now we would want to see other form of response. Okay, here we will notice that this is an undamped response. Okay, you never damp out, right? And if this never damps out problem, remember we mentioned that the real part, okay, will tells us the envelope of our exponential decay. So if this real part doesn't exist anymore, okay, the real part is 0, then it will not damp, right? That is the characteristics of the systems, right? So if now our solution doesn't have the real part, okay, when we solve this one, we get the S solutions is an imaginary value without any real part, right? So in that case, we will get this undamped response, right? And the corresponding time response would be the K, right, due to the 1 over S, and this part, okay, since we don't have the real part, okay, so we don't have the exponential component over there, right? We don't need to multiply by the exponential term is disappearing, right? Only the imaginary part, okay, that we can put it in, right? The last type of second order response would be the critically damped response. Okay, this is where the response is damped at the fastest. Okay, the response is the fastest possible and without a overshoot. Okay, you don't have overshooting more than the final value, right? What we can see is that in this critically damped, now this pole, okay, before that, if we want to have a overdamped response, we will have two real pole. Okay, if these two real pole now going to a very close, okay, and found to be the same solution, same value, okay, when this is the same value, then we will approach what we call this critically damped response. Okay, so meaning to say, if the solutions for our denominator at the bottom is a real equal pool, then you will get critically damped response, right? So this is a critically damped response, and the value will be E minus 3t plus K3. You need to add a t over here since you repeat 2 times, okay, remember, right? So E minus 3t again, right? So this is a summary of the 4 type of response that you may get when your system is a second order system, right? And this is the comparisons between them. Okay, undamped, you have the overshoot, right? Whereas the critically damped and underdamped, you don't have the overshoot, right? But then you can see the characteristic, it will always start with a slow down and then up, right? Okay. So what are the 2 parameters that control the behavior, okay, of these things? Okay, for the first order, we have the time constant. For the second order, we have 2 terms. One is, we call it as natural frequency, and the second one will be the damping ratio, right? So the natural frequency for second order systems is the frequency of the oscillations, okay, assuming no damping, right? That would be the natural one, right? Then we add in the damping ratio to describe the whole system, how it behaves under the damping, right? And this damping ratios is defined by the exponential decay frequency divided by the natural frequency, right? And if we transform this, okay, we will get 1 over 2 pi divided by the natural period. Okay, remember, period and frequency, there is a conversions, right? Okay, which is inversely proportional, right? So you have the natural period divided by the exponential time constant. Remember time constant? Okay, the exponential time constant, right? The minus AT part, right? The A is the time constant of the decaying envelope, right? So you can also get that damping ratio from this easier form, right? So this damping ratio have a characteristic is that it remain constant regardless of the time scale. Okay, even you are mentioning about millisecond or millennium, or yeah, no matter how long it is, okay, using a same damping ratio, the frequency would be the same, right? We would call this as 3 cycle in a millennium or 3 cycle in a millisecond. They have the same damping ratio. Okay, we are referring to that. Okay, so regardless of the time. Now how we can transform this general second order system into that two parameter. Remember the natural frequency and the damping ratio. How we can form that, okay, so that we can control it later on, is that without the damping, the response will be mainly due to the natural frequency, right? So because of that, we assume this part, okay, the middle term, okay, in the second order polynomial to be 0. Okay, when this is 0, then it will be purely no damping, right? So when this is purely no damping, then we will notice that this is equals to b, right? So we can put that as omega n square equals to b, or omega n equals to square root b. Okay, your square root b here, right? So that would be your b. So if you want, we can now start to substitute this into here, right? Omega n into the position of b, right? Then once we have the omega n, the natural frequency, into the positions of b, right? Now we would also want to construct this second term, okay? So this second term, if we notice in a second order polynomial, the second term is actually 2 multiplied by something, right? And the other part would be from the c, right? This part, right? And s plus c. So we can actually combine these two together, okay? So that they are related, and they are also related to the damping ratio, okay? So based on these definitions of damping ratio, we can regenerate, okay, rearrange, and such that the A is equals to 2 damping ratio omega n, and that would be our equations, right? So once we have these equations, now our solutions would be purely in this form, right? This is minus b plus minus b square root of b square minus 4ac, right? Whereas the 4ac, when you do this, is actually become 1, right? Immediately you can solve it, right, by looking at the damping ratio and the natural frequency, right? And from that onwards, okay, it would be much more easier for us to describe the damping. Okay, now we only look at the damping ratio. Okay, when the damping ratio is equals to 0, okay, damping ratio equals to 0 means no damping, right? So when it is no damping, then our pool will lies on the imaginary, and we get this no undamped response. When the system have a damping ratio between 0 to 1, okay, it's still under damping, okay, then you will have a complex solution, okay, complex value, okay, with a real part, okay, and then when it is equals to 1, now it is now critical, right? The damping ratio is become critical. At this equals to 1, then they have a equal real solutions, okay, and when it is more than 1, then it will start to break into two real pool, and you have an overdamped response, right? So it's much more easier for you to visualize, okay, through this damping ratio instead of using the previous method, okay. This is an example, okay, how you can actually find the damping ratio and the natural frequency, okay. We know that once this is equals, then we can get the natural frequency, okay, of this, which is equals to 6, and then we know this part will be 2 damping ratio multiplied by natural frequency. Natural frequency is 6, then you will get the damping ratio as 0.35, okay. Once we know this is 0.35, okay, immediately we know that this is under damping, right? There is damping, so it's under damping. It's not over 1, so it's not over damping, okay. It is under damping, right? So very straightforward. You can try it with this examples, okay, to test your understanding, right? Next would be the underdamped second order, okay. How we now want to check the transient response of it, okay, how it behave. Like the first order, we have the settling time, the rise time, right? Same thing for the second order system. We would want to know all these things, okay. So we would start using an underdamped systems to represent a second order system, right? So we use the second order underdamped system, okay, to check, okay, how it would looks like, right? So when it is underdamped, it should be less than 1, okay. The damping ratio should be less than 1, and our equations would be in this form, right? So it looks complicated, but actually you just have to fill in the blank. That's it. Okay, very straightforward. Okay, we will not go through in detail on that. You can slowly look at the step on that, right? How you can fill it in based on the damping ratio and the natural frequency, right? So now come to this, how it would looks like, okay. This is how it looks like when we increase the damping ratio. It changed from the underdamped, okay, undamped to underdamped to critically damped, okay, when this is equals to 1, and to overdamped, right? So this is when I try to maintain and plot the graph by maintaining the natural frequency, okay. By putting a damping ratio, changing the damping ratio, the behavior change, right? So you can see that by changing the damping ratio, by lowering the damping ratio, you can see more oscillations, right? You can see the more oscillations, but then it doesn't actually affect the natural response, okay, in terms of time, right? So you can see that they are still oscillating and peak, okay, almost similar, okay, at the similar time. All right. So here is the definitions of others parameter, okay, to represent the performance of a second order. So first thing is the rise time. The definition of the rise time is remain the same from 0.1 to 0.9 of the final value, okay, how long it takes. Okay, so what you need to do, just from the curve, plot it out, right? Take 0.1 to 0.9, okay, and measure what is the time, okay, between them. Then for the peak time, you will see that the peak time usually peak at the first oscillations, okay. This is the maximum peak value, or the peak value itself, okay, and that corresponding to the peak time, so you can measure how long it takes to reach the peak time. Then the fourth one will be the settling time. Settling time, remember, we have defined the settling value as 2% from the final value, okay, and this is where it's become important, right? So we would draw a 2% range, okay, 0.98 and 1.02, a range of it, and you will see that this will start to oscillate, okay. You have to check which part it will no longer after that over than this range, okay. It can be going up again and then fall down, okay. So it depends on which line it touch, right? So from that point onwards, okay, you will draw a line and measure what is the settling time, okay. So these three will represent the characteristics of second order undamped response, okay. Then for the third for the fourth performance characteristics would be the percent overshoot, okay. This percent overshoot is when your system have overshoot characteristic, okay. You overshoot it, right? So meaning to say, for critically damped and overdamped, you don't have this percent overshoot, okay. They don't overshoot anymore, right? But then if there is an overshoot, then we will define this percent overshoot as the amount of waveform overshoot from the steady state, okay. So here we assume the steady state will be our final value, okay, and how much it's overshoot, okay, the value of it, okay, the percent of it, okay, away from the steady state value, right? The rise time, peak time, settling time basically represent how fast is the transient response, okay. And this information helps the designer to see, okay, whether the speed is good enough or not, okay, or whether it will actually affect the comfort of the designs, or yeah, depends on what you want, okay. Sometimes you want it fast, okay, sometimes you want comfort and so on. So this will tells us the transient is it of the response, right? To evaluate the peak time, actually we can analytically solve it, right? And for a second order system, when we solve this peak time, we eventually get this value, okay. The peak time is equals to okay, to pi divided by the natural frequency square root of 1 minus damping ratio square, okay. So analytically we can solve for the peak time, right? So if you want, okay, you can again go through the derivation of this, okay. We will not go through in details here. The only thing is that if we want to evaluate or to identify what is the peak time, you can calculate, okay, instead of measuring it from the curve. Then also if we want to evaluate the percent overshoot, alright, then you can have this value, right? Percent overshoot, okay, wait, it's lagging, okay. So now in the percent overshoot, okay, you will calculate what is the maximum value, okay, maximum value, right? And then you minus the minimum overshoot value, okay, or minimum value, right? So here, since it start from 0, so your minimum value will be here, right? And divide by your final value, right? So you will get your overshoot percentage, right? Then also since we can mathematically solve this, right, when the unit step is given, then therefore for that final value equals to 1, then the percent overshoot can be calculated mainly depend on the damping ratio. You can see that this equation mainly depends on the damping ratio, right? So the percent overshoot is depending on the damping ratio. By tuning the damping ratio, we can control the percent overshoot. When the damping ratio is very high, it will no longer overshoot, right? That is when the critically damped system, their overshoot is 0, right? Okay, so this is how it looks like, right? When the critically damped correct value, which corresponding to a damping ratio of 1, the percent overshoot now become 0. Okay, whereas when we don't put any damping ratio, okay, means damping ratio is equals to 0, then it will continuously oscillate, okay, then that values would be 100%, right? So this is the relationship between them.